In this lecture we're going to look at computer memory and storage. We're going to see there's a basic storage hierarchy which goes from memory on the CPU itself and the main RAM of a computer through to offline storage such as tape and optical media backups. Early computer memory used something called magnetic core memory. This card would be about 10 centimeters aside. And if we look closely at what's in the centre there, we would find lots of little magnets, little magnetic cores with wires in between them. The magnets could store a charge, and you could set a particular magnet's charge to store a value or to clear the charge stored in the magnet. And that gave you a basic storage capability. Magnetic cores were incredibly stable. Indeed, magnetic core memory was still used in the early space shuttle because it was a very reliable technology, a very well understood technology, and very resistant to damage and could maintain the contents of the memory even when power was switched off. So it actually retained its memory for a very long period of time. But it's not really used in modern computing systems at all. Instead, what we find is DRAM, or dynamic RAM. Here we can see some different DRAM chips and modules from a number of different years and eras. The more recent memory modules on the right, which as you can see contain a number of different DRAM chips in one circuit board that just slots into the computer. So modern DRAM modules may contain quite large capacities, up to several gigabytes in one memory module, whereas earlier memory module chips might have only contained a few K of RAM on an individual chip. All DRAM follows a very similar operating principle, which is highlighted in this rather complex diagram here. And that if we look at the boxed area, we can see there is a transistor and a capacitor. So here's the transistor here, it's a capacitor here. And a capacitor is an electrical device that is able to store a charge for a period of time. So the individual memory cell is very simple. It's got two components, a transistor and a capacitor. We have a row of these components connected together along a word or address line. That will connect all the cells in each row. And there are also, there's only one shown here in green, but there are two data lines connecting all the cells in each column. So by setting the circuits, so by setting a value to activate a particular address line and setting a value to activate a particular column, then you can address an individual memory cell, an individual bit of memory. So each of these cells in red is going to store a single 0 or 1 value. And if we know which address line it's in, if we know which column it's in, then we can address and refer to that one cell. So for reading and writing, the signal is sent to make one address line active at a time. Then when we're reading, normally we would read a whole word at a time. So what would normally happen is you make one address line active and you copy all of the bits down at the same time. And so this cell here, its value is copied down, and it's copied down to this sense amplifier here it's called, but it's basically a buffer that just stores the values that have been copied from the RAM. When we're doing a write operation, it's basically the same idea. We put values into the buffer, we activate the lines, and with a particular active address line, that switches on the transistors so that they can receive the charge that we're sending up the line. So in the read state, we activate the address line, signals are sent down, and the zeros or ones are copied from each memory cell into the sense amplifier. In the write operation, the values are stored in the sense amplifier and then sent up the address lines to the memory cells. There are some problems with DRAM, however. Capacitors lose charge over time, and the very small capacitors that are created in silicon chips lose their charge quite rapidly. So the memory cells need to be refreshed, so we need to put more electricity in just to keep the memory the capacitor contents the same as they are. And the current standards for DRAM typically require memory cells to be refreshed every 64 milliseconds. It's also possible that magnetic and radiation interference can cause a bit to flip randomly. So more expensive DRAM is available that uses some sort of parity checking or error correcting code. These DRAM modules generally cost a little bit more because it adds extra circuitry, so the memory in the system cost will be higher. And for a lot of systems you will find that you are able to buy memory modules with or without error correcting code, and the error correcting code chips and modules will normally cost a bit more than the modules without. For most home computer use, it's okay to do without the error correcting code. The random bit flip is not very common, but in servers and other situations in business systems it can be quite important. SRAM is static RAM. Unlike DRAM, static RAM doesn't need refreshed. It keeps the value that's been stored in it. When power is switched off altogether, the cells will lose the value that's stored. But as long as the power is on, you don't need to refresh the cell, it's going to keep the value. And it's built out of typically 6 or more transistors. And you can see one of the circuits here, so it's clearly a lot more complicated. There's more circuitry involved. More circuitry means that the chips are more expensive, they can be faster, and they use less power than DRAM because you don't need to refresh them. And they can be easier to integrate into some systems because there's no need for special circuitry to refresh the memory. For long-term storage, RAM is relatively expensive and power hungry. It's good for storing active programs in a running computer. It's very wasteful for storing inactive programs and data, and it's completely useless for storing anything that needs to be kept when the power is off. And so we have a range of different storage media which we're going to look at. We also have cache memory, and we cover this elsewhere in the course, but the general principle for cache is that a small amount of high performance memory can act as a local copy of some data that's stored in a cheaper but slower memory form. So for example, most CPUs have a cache that store some of the program data from main memory. And that allows the CPU to operate on that memory at full speed and only needs to slow down when it needs to get another chunk of data from main memory. Or disk drives, especially hard disks, may use RAM chips to cache some of the data that's been recently used or accessed to try and limit the dependency on using the disk itself to read and write data to allow faster access. Quite obsolete now, but we looked in class at some of the floppy disk formats, and here we can see 8-inch, 5¼ and 3½ floppy disks. 3½ floppy disks were still in regular use until probably around about 5 or 10 years ago. They're quite rare to see nowadays. What these media all have in common is that inside them they have a flexible disk that's covered in magnetic particles. If you think of it, little tiny bits of iron filings, for example. And typical capacities of a 3½ floppy disk are typically from 1.44 megabytes to just under 3 megabytes. And most floppy disks were very similar in their operation. You would have some kind of disk disk hub, which is used so that a mechanical arm could slot in there and actually spin it at high speeds. The 3½ disks introduced a protective shutter, so you didn't need to use an extra sleeve to carry the disk around in, so the shutter provides protection for the disk surface itself. The 3½ disks also introduced a hard plastic housing, so although they're called floppy disks, the cases are quite firm and hard. Inside of that, there's a polyester sheet, so it's just a sheet of some fabric that allows the disk to rotate rapidly without damaging itself or scratching. And the disk itself is coated in magnetic particles, and the whole readable area is broken up into a number of tracks and sectors. You can see a red area indicating one data sector. What's worth noting in most floppy disk formats is that the sectors are arranged so that it's the same angle of rotation for every sector. So it's the same angle of rotation. So this sector here in the centre of the disk actually has a much smaller area than this sector here at the outside edge, but they each contain the same amount of data. And that was simply because it was easier to develop the mechanical devices that could read and write, mechanical and circuitry to read and write the data by turning the disk at a constant speed. There's actually, because of the distribution of magnetic particles, it would be possible to actually put more data on the outside edge because there's more area to use. But that would involve having to be able to reduce the speed at which the disk turns the further out from the centre the data is. And that was a little bit complicated for earlier floppy disks to do now. That sort of technology is very easily available now and is used in other media, such as hard disks. With hard disks, the data is stored on hard, non-magnetic platter. So we've got a platter of some non-magnetic material that's covered in magnetic particles. The read heads, platters and the control circuitry are all contained inside a single sealed device. So normally these devices, hard disks, are sealed, completely sealed, so you can't get in and you can't actually see what's inside, but this one's happily been opened up for us to see. Here, this is the disk head, this tiny device here, just floating just a minuscule distance above the surface. It's not touching the surface, it's just above it. And so we can have a read or write head, and there's two key ways in which you can do this, longitudinal or perpendicular, but either of these, what it's essentially doing is making the magnetic particles line up one way or the other way. And depending whether they're lined up one way or the other, that indicates whether it represents a 0 or a 1. Longitudinal recording, the bits are aligned along the surface, so the flow of the magnetic field is along the surface. Perpendicular recording aligns the direction of the magnetic charge vertically, which actually allows more data to be packed into a smaller area, so it's a more recent innovation and allows more data to be packed more tightly. It does require a stronger charge, stronger current. Here's a close-up of the disk head, the read-write head, and it really is hard to appreciate just how tiny the distance is from the point to the surface. The platters themselves are coated with a thin layer of magnetic material, and we are talking about around about 15 nanometers of material. Typical rotation speed is about 7,200 rotations per minute, or revolutions per minute, and the heads float just nanometers above the surface. So we're talking about particles of smoke wouldn't be able to fit through the gap. So the modern disks are sealed out and completely airtight. Earlier hard disks were quite different, so if we go way back to the 1970s, hard disks had removable disk packs of the platters, and the drives would be these giant devices about the size of a washing machine. You could put in one pack of disks into it, whereas the head would be in the drive, which would be a separate device. There's a number of issues that relate to hard disks in terms of the performance that can be achieved from them. Most hard disk drives will switch off automatically to save power, which means that when you start to use a hard disk after a period of not using one, it takes a little bit of time to start up, so some spin up time. And data can be distributed across the disk in a wide range of locations. So when you go to read or write some values, the hard disk head may have to move about So it might be in the centre of the disk and it might have to move out to the edge. So there's some kind of seek time. And latency again, because the disk may have to rotate until you reach the correct point on the surface of the disk. And then there's fragmentation, which is that single files can actually be stored in different locations scattered over the surface of a disk. So that might add additional time as the disk head has to move, as the drive head has to move between different sections and positions. However, there's a range of different things that people have done to improve speed and technology. And so the revolutions per minute for server disks can be well over 10,000 RPM. Notebook disks, to save power, are typically slower. And when you measure all the different delays together, that's often referred to as the average access time. Sometimes also referred to as latency, which can be confusing. And the speed is usually measured in terms of burst speed and transfer rate. So burst speed is what's the maximum speed you can get. When the disk head is over the data and it's reading the data you actually want, what's the maximum speed you're going to be able to get from a particular hard disk when you've taken out the seek time type errors and delays. So some typical disk drive stats that are current. Capacity for a hard drive is anywhere from 500 gigabytes to 2 terabytes. It can actually be larger or obviously smaller. Those are quite typical for current devices. Spin up time could take several seconds. Seek time 5 to 10 milliseconds. Average access time and latency 3 to 6 milliseconds. Data transfer rate round about anywhere from 250 to 350 megabytes per second. Higher performance disks are available at a cost. And then there is tape. Now, you only really see tape drives in 70s films. So in a Bond film or some other film where there's a government research station, you may find rooms full of computing devices and these sort of taped machines at the back of a room, just going forwards and backwards as they read and write to a particular tape. Tape gives you a sort of sequential data store. It's very slow for random access because it's very slow to move from one point on a tape to somewhere at the other end of the tape. It takes a long time. But they can have very high speed when it comes to actually saving or restoring data in order. So as long as you don't have to move from one position to another, as long as you're able to just keep saving to the tape, turning it as you go, so you're doing everything in order, you can actually have very high speeds for saving or restoring data that's been stored in sequence. And tape is still used for data archiving. So although it might seem outdated and we don't see it very often in the systems we use here at university, and you don't tend to see it very often in computer shops or in magazines, it is still used for servers and for internet service providers and for other people who've got huge volumes of data to store. Tape is still used because it's very cheap. And capacities allow you to have, for example, tape cartridges where one cartridge can store up to about 5 terabytes. And that's quite current today. So one tape cartridge will store more than a hard disk, but will be cheaper than the comparable hard disk. Another media that perhaps has only got a limited lifespan left is optical discs. CD, DVD and Blu-ray. They all use lasers to etch and scan microscopic holes or bumps on the internal surface of the discs. And they all use a transparent layer that protects the surface, that makes them resistant to minor scratches. You can see that the capacity of these devices has gone up over the years. 640 then 700 megabytes for CD, just under 5 gigabytes for DVD, and up to 50 gigabytes for Blu-ray discs. And they all follow roughly this basic pattern. They have the bottom layer here is a hard layer basically that just protects the disk, protects the read-write surface. Above that, at B, is a shiny layer that reflects the laser. And data is encoded in that layer in pits and bumps in the reflective layer. On the other side of that we have an extra layer to protect the other side of the reflective layer, and then on top of that we may have some artwork or imagery or text or just a label area on the top of the disk. Data is read from and written to by means of a laser beam. So for a CD, for example, we'll have a red laser beam that reads a CD and is reflected back to a sensor, which converts the light that's reflected back into electronic data. CD, DVD and Blu-ray all use a spiral track with constant track size, so the data spirals out from the centre of the disk. And with the principle that the smaller the wavelength of the light, the more tracks can be packed onto the disk, because you're able to pick up smaller and smaller bumps. You're able to detect smaller bumps with a smaller wavelength of light. Blue light has the shortest wavelength out of red and blue, and so where CD and DVD used red lasers, the blue lasers and Blu-ray are able to encode and detect data in much smaller areas. Both DVD and Blu-ray have what's called a dual layer format, which allows lasers to focus onto one of two layers on the same side of a disk, which effectively doubles the possible capacity. Optical media also has a number of read-write formats. It uses a special dye layer before the reflective layer that can have pits burned into it by the writer. But the write drives can produce a higher power beams that mark, melt or distort the dye layer. And there are lots of different disk formats for optical media, such as write once formats, plus or minus R. So those are disks that you can write to, but once they've been written to, you can't change the content. And rewritable disk formats. The dye can decay, which would affect the lifespan of the disk, but modern disks should last anywhere from tens to hundreds of years. But an effective backup policy is always important. But modern media is moving away from a whole range of different disk formats and increasingly moving to things like flash storage. We can see a wide range of different flash cards and USB memory sticks here, all placed next to, for comparison, a portable hard drive. And capacities have really grown significantly. So some of the devices here, we have a 16 megabyte SD card next to a 1 gigabyte Memory Stick Pro, next to some USB sticks. And USB sticks of this size may now typically have 2, 4 or 8 gigabytes, and higher capacity devices are available. By comparison, this hard disk has got 64 gigabytes. It's now possible to buy USB sticks with larger capacity than that. So we can see some of the typical capacities again here. So what's flash memory? Again, it uses transistors, but unlike normal DRAM, we have an extra insulated connection and an additional gate that can actually store the charge for a long period of time, for years. And that allows flash RAM to store data without power. An issue with flash RAM though is that individual memory cells fail over time. This is called memory wear. Anywhere between 100,000 to 1 million program erase cycles, so program is when you put data in, erase is when you clear it. So after 100,000 read writes, or up to 1 million rewrites of data that's on your flash device, you may start to experience memory loss. To try and limit the effect of this, most flash devices use something called wear leveling and memory block management to extend the lifetime. What this means is that if you save a file on a flash memory stick, you edit the file and save it again, it will probably actually save it somewhere else on the flash memory so that it won't wear out the same memory locations. Using flash as cache memory for your computer or using flash memory for compiling on can cause serious damage quite rapidly, because when you compile programs, you do lots of read-write operations, and over a period of time you might be surprised how quickly you can really affect the flash memory just by using it as a disk when you're actually compiling projects regularly. There's a wide range of speeds and lifetimes of flash memory and costs. So you will see bargain flash memory with high capacities for low prices, and often that will actually be flash memory with a much lower speed rating, and it may not offer as good a lifetime as some more expensive flash memory. Solid state drives are quite a relatively recent innovation and introduction, and they use RAM as hard disk. Usually flash memory, DRAM solid state drives are possible, but these would need to constantly powered. Higher performance and cost than normal disk drives, but lower capacity, but also lower power use, so good for laptops. Memory where still an issue can be paired up with a normal hard drive, where, for example, you place primarily the operating system files into the SSD, so it's got a very fast boot up and startup time, but user files and memory cache may be in the hard disk. So some comparison of SSD versus HD. SSD will spin up instantly, there's no spin up time, there's nothing to spin. Seek time will be incredibly low because it actually knows where the data is. Latency, effectively low. Fragmentation, well, data will be fragmented in SSD, but it won't have any effect. Typical transfer rates for SSD and HD, though, are often quite similar in range, but by having no effect of the fragmentation, by reducing all the different latencies, SSDs can operate much, much faster. You can also get some performance SSDs with much higher transfer rates. And the cost is the kicker, with SSDs currently costing around about £1 per gigabyte, and hard drives costing a fraction of that. Which brings us to the cost versus speed comparison for these different devices, where DRAM is clearly the most expensive, it's the peak of the blue line, but is the fastest. It's got the fastest seek time in milliseconds shown here. Flash is still pretty expensive and pretty fast, but not as fast as flash. Hard disks getting pretty cheap now, but there's a much bigger speed delay. Tape, cheapest chips, very slow. And you note that this scale here is logarithmic. So for DRAM, we're in fractions of a millisecond of seek time, and we get up to hard drives, we may be up to some number of milliseconds, maybe 10 milliseconds. When we get up to tape, we're certainly in tens of thousands of milliseconds. Lots more reading in Wikipedia as usual on computer data storage, and lots of related articles on all of the technologies that have been covered in this lecture, and more in Principles of Computer Hardware in Chapter 12 on computer memory. Lots of credits from all the images used in this lecture, mostly sourced from Wikipedia or the Wikimedia Commons.